All right. So, good story from yesterday. I almost got shot.
What? Yes.
I
mean, context of where is most important.
It's even better. Where? So I was playing golf at Black Wolf Run, like a $275 person golf course. And my buddy and I, we played golf all summer on this thing called the Platinum Passport, and it gives us like two rounds of golf at a bunch of places. You just have to pay for cart. And Black Wolf Run is on there, but you have to either play super early season or super late season. So that's why we're playing on November 1st. So we were already being treated like second-class citizens because we played the $275 course for $30 a piece. We just had to pay for the cart. Well, apparently there's a hunting lodge. I don't know if it's owned by American Club and the Kohler Experience or if it just happens to be butt up against the course, but we're on hole number 8 on this course. And keep coming up to this point, we keep hearing gunshots. All right? And, so we just assume it must be hunters, right? I'm not a hunter, but I know it's like some hunting season, ducks or whatever. No, these were birds they were hunting.
Oh, yeah. It is
whatever, I mean, yeah.
Turkey.
So we get to hole 8, we actually see the hunters out there. There's guys out there in this field, like right next to the tee box, right? They're 300 yards from us. And we see their dog traipsing through the... So we see the dog kind of running towards us, and all of a sudden this bird flies up into the air. They're aiming at us. All right?
Presence.
Okay? I'm standing here. There's a... probably where that TV is. Okay? So not right next to me. Close enough next to me, right? The TV explodes. Okay? The whole number 8 sign at Black Wolf Run, gone. Okay? Just shatters into wood. Okay? The hunters, they just wave.
How far away were they?
300 yards? 200 yards? I mean, like, you could identify, like, the dog pretty easily.
That's definitely
You're talking 150 yards.
To spread out.
You're talking 150 yards minimum. That's going to explode.
Yeah, so, you could see their dog and stuff, right? Because we're on, like, an elevated tee box.
Yeah.
So I mean, whatever. I don't know anything about this world. I don't hunt, but in any case, like you could hear them like whistling at their dog and stuff. They were close enough for that. Okay. So so this like ticks me off, right? So I'm like, and I don't get mad very easily, and so I go in afterwards, and I'm telling the clubhouse people that okay, your hole number 8 sign is destroyed, okay. And I'm like, we got shot at on the course. They act like it was no big deal. It's like, oh yeah, we got some hunters. I almost got shot on your golf course. Yeah, so I gave them a less than good review on Yelp.
Don't go on hole number 8 in the late season. You might get shot.
Plus, I have no idea why they charge so much for that course. I mean, no course is worth that much anyways, but like Whistling Straits, which is also part of the Kohler Experience thing up there, I mean, you're going to spend $500 there after you pay your caddy, and no course is worth $500, but if any course is worth $500, it's Whistling Straits. And if this is like their course they say is like almost as good, if Whistling Straits is a 10, this place is like a 2. Okay, so something like that. Yeah, I don't know, but I kind of wish I had gotten hit though. I mean, I don't want to die, but like, late season, I'm not going to be golfing too much more. Sustain a couple injuries, that would be a great place to sue.
Oh, yeah.
Yeah, it's like, look, I got shot while golfing on your course.
What are they going to do about that, No, it's your fault. Well, no, it wasn't.
What?
I didn't know I was supposed to wear orange on your course.
What are they going to do about it?
Yeah.
Pay me?
Yeah, exactly.
Yeah, I mean, right. I mean,
what defense do they have?
Well, they wouldn't want it to go to court. I mean, that's what I'm saying.
The
Kohler Experience is like a worldwide destination. That same guy owns St. Andrews over in Scotland. There's some bucks floating around there. So one dude gets shot in the course, probably not going to become a public spectacle. There's probably just going to be a check written. Right?
You wouldn't be the first person to get shot on that.
I guess how many of you in here are hunters? I mean, there are a couple of you, right? Okay, I mean, I guess what maybe ticked me off more was the fact that they saw the sign blow up and they just kind of waved at us like, "Oh, I'm sorry."
How much beer were they drinking? That's a
Doesn't
bad
matter.
hunter.
I mean, okay, mistakes happen. Okay, it's like,
At least we're
gun
not
went
being
off,
like, "Oh, shit."
nobody died, sign got destroyed. Could have been a lot worse. Okay, you run up there, make sure everybody's okay. You apologize profusely. You don't just wave like "oops," and then give a treat to your dog.
You said these guys were how far away? 300?
I mean, I'm on like an elevated T, so it was hard to. I mean,
Hard to say.
yeah, they were not far away. I mean, I could see their dog clearly, like even his little legs and stuff. You know, like because the dogs, I guess, aren't that big.
No.
The hunting dogs, so you know, like
50, 70 pounds.
yeah, you could hear them like talking to the dog. So they were close enough where
Okay.
you know they were right there.
If they were a ways away, it's like, what are they hunting? Rifles? I mean, that's the only way.
Yeah.
Sounds like they're
I-
hunting, so full choke shotgun.
Birds with birdshot.
Yeah.
Birdshot doesn't travel more than like 150 yards.
Okay.
Yeah.
I don't know anything about hunting.
Yeah.
So
That's why I'm saying 150.
yeah.
That's,
So
that's scarier close because you know it's a shotgun.
Yeah.
I mean, so I understand it spreads out that way because you know
Yeah.
Yeah,
you
but,
hit-
but with birdshot, it's supposed to stay really. It's got a pattern. To
kind
it.
of a cone.
Yeah, it's
Yeah.
supposed to stay really small.
Okay, but it so at 150 yards, I mean, it still
It's
can do
still-
damage.
Yeah, but it should be spread out enough by then. So if it blew up a sign, I'm guessing it was pretty close.
Yeah, like
Okay.
100 yards maybe.
Yeah, I mean, it was just a wood. I mean, you know, a wood T sign, right? Tell you what the sign was.
Yeah.
So it must just have been they hit it dead center or something,
Yeah.
and it just, you know, with a cone of that, it just was enough to shrapnelize the wood. Yeah, it freaked us out.
Jeff
Pretty bad.
You should have shit yourself.
That's recorded.
Would have been another lawsuit.
Oh gosh. Okay, so let's figure out where we left off. So I think we brought our code up to date last time, right? With the context switching. So I think we need to introduce a couple more things before we dive back to code. So let's kind of get back over here to the slides for a little bit. Let's see where we kind of left off. Because I know I kind of gone out of order because I say stuff and then we catch up to it with the slides and that stuff. So, all right, context switching there. We've done our Q stuff. That's there. Okay, so this is that stuff. All right, so this is kind of showing an implementation of the those queues. So we see that we kind of chose the right thing. We chose linked lists for our queues, and you know this kind of looks linked listy. You know, heads and tails, and we don't know where it starts. And here's each of these PCBs, and among the things that are in the PCB is a collection of registers and all that jazz. Okay, so this kind of gives us a visual telling us the data structures we should have used, which are equivalent to the data structures we did use. Okay, so yeah, here's the representation of process scheduling. So process scheduling is our long-term scheduler, as opposed to our short-term scheduler being the CPU scheduler, that dude that needs to be really, 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 really fast. Okay, so what's this guy doing? Well, he has his ready queue, which feeds right into the CPU. He has his IO queue. Actually, this is funny. Hasn't the book been calling this the device queue?
Yeah.
But I always call it the IO queue. Or what a waiting queue. I call it the waiting queue. Well, at very least, this is closer to my version. Well, at least not equal to their version. Can't even be consistent. It's the whole dinosaur prehistoric thing. It's screwing them up. Okay, so this is waiting for I/O. So that's where you leave the CPU. So you've interrupted, but you're not getting back into the ready queue. Now you're in the I/O queue. Or your time slice has expired. So this is the various reasons why you've left the CPU. So you know, you can't continue on with your program because of an I/O request. You can't continue on with your program because your time slice on the CPU has expired. You can't continue on the CPU because you're forking a child in a box. Okay, you're forking a child in a box is what you're doing.
It says child executes and not executed.
That would have been a heck of a typo.
Child executed.
Somebody's reading
Actually,
a rough draft for these slides and was going, "What are you doing?"
When was this? Were any of you at the? Oh, you used your cane. I thought that was like a little axe. It's like, what the heck does the Palestinian kid have an axe for?
Beheading. Of course.
Are you feeling better?
No.
Is that really your voice right now? Are you doing lunch today? I want to hear all about it. I mean, in detail. A lot of detail. What was I about to say? Oh, I was talking about, were any of you in here at the Chicago Hackathon, not this past year, but 2 years ago? That was the one where we, our group did a thing where we were crowdfunding child sponsorships. So the idea was, you'd have, we go over to other countries and you have, children that you give money to, like we give $25 a month to a couple different kids somewhere or something like that. And the idea is there might be a lot of people who are willing to give $1 that can't give 30, something like that. So if you can get 30 people each willing to give $1, that will help people, right? So, but we had two versions of the app. One where you take a picture of the person, like almost creating your inventory, right? And then the other one would be the thing that the Americans would use for shopping, picking the kid, the one that's closest to being fully sponsored, and then funding that one. Well, when we were putting together our presentation, this is what kind of reminded me of the forking a child thing. We were working on very low sleep. We had this diagram of how the thing worked, and there was, in this diagram, we had a baby dropping into a blender, and there was a shopping cart or something like that. I don't know, it just reminded me of the baby in the blender thing with the forking a child. Yeah, but the funny thing is, we were kind of joking about it, like when we were doing it, we were just messing with the present. It totally made it into the final presentation. So we're flipping through our slides, and we get to this final slide that's like literally showing like kind of like, the pattern of how the app works. It shows this lady that basically has a kid that falls into a blender, and then
Wasn't there a video of it or something?
I think
you showed it one time in class in 250.
it was awesome.
What was the reaction?
Everybody started laughing. Nobody was had any sleep. All right, so you leave the CPU for I/O requests because you ran out of time, because you've given in to certain impulses. Oh, that's terrible. Or you're waiting for an interrupt. So there's something else that kind of needs you to not continue. That could be like multi-threading type stuff. So if you're a thread within a single process and you can't continue on until something else finishes from within that same process, you'll get interrupted. So they kick you off the CPU because you can't continue on with your current task until something else happens. So a couple different ways you get booted off the CPU. Okay, things we've already kind of talked about, but this is a visual of it. Okay, so then we have our Pac-Man stuff, so we were kind of showing how that worked. Those are our two different schedulers. All right, so we can look at a medium-term scheduler, so something kind of in the middle. So we have swapping in, swapping out. So this is our context switching stuff. Then we have our CPU, ready queue feeding directly into our CPU. The swapping in, swapping out, this middle scheduler is kind of handling just context switching. So we've really split that CPU scheduler into two pieces. One is feeding off the queues. The other one is handling the packing your bags and unpacking your bags. I'm not sure it's really solving that big of a problem, but book thinks it is. Okay, so we've talked about context switching. We talked about the difference between spawning a thread and creating a process. Processes are all uniquely identified on the operating system by a process ID. So that's kind of their unique phone number, if you will, where threads do not necessarily, well, threads do have an ID, but it's an ID that's completely governed by their parent process, because threads exist all within inside a single process. A process also has address space associated with it. This is where it lives in actual memory, and this is where a child is originally duplicated when they fork, but then the process then gets scheduled on its own, so it's going to get its own address space. So here's some system calls. So fork creates a new process. So exec is after a fork to replace the process's memory space with the new program. This is kind of what I just said, right? So when a process gives birth to a clone of itself, creates a child process, that originally happens within the memory space of the original process. Then when we execute the new process that was born, it's then essentially a full-fledged process and gets its own space in memory and all that jazz.
Totally explain how kids are made by children that way.
Right. This is how babies are made, people. All right. Yeah. So this is kind of the picture of that. And I think this is kind of a code example I've referenced before. This idea. This is where the actual forking takes place. Okay, right here. So if the process ID is less than 0, then something happened. Okay, we in spawning the new. Else if we're equal to 0, that means we are the child process. Okay, so if our process so fork always returns a process ID. Okay, it returns something less than 0 if something bad happened. It returns something equal to 0 if we're the clone, or it returns the original process ID if we're the parent. Go ahead.
So the process ID itself is like it's its own class or struct?
I think actually process ID is just a int. Well, no, it is a struct right here. Yep. PID underscore T. That's kind of a common thing for a struct. So I'm sure this is probably, my guess is it's an enumerated type of type int. We can look it up here real quick. PID underscore T. Here it is.
One line.
Why? Just why? Yeah, my guess is it's an enumerated type. Is a signed integer type, which is capable of representing a process. The question is why does it need to be signed? We would never have a process ID that's negative. So in a language like C, this should really be an unsigned, depending on what the maximum size process ID you're willing to have, either an unsigned int or an unsigned long, something like that. Yeah, so this was probably something that was written a long time ago and has just been survived. I'm sure it's not written this way in Windows. Windows, I bet you their process ID is a unsigned integer. They might still have a special name associated with it, but why? Yeah, in other languages, this is usually called an enumerated type. Yeah, they don't actually tell me what kind of animal it is here, but something like that. Okay, so this would be kind of an example of a program that forks. So understand that this actually causes your, a program that forks actually causes your program to be kind of monolithic in nature. You might have this gigantic source code file because, first of all, in C, you would have this idea here. You don't have objects. You can't spawn off something else and say go and start doing your thing. So this is all kind of in one sort of monolithic file. one gigantic file, and then you have to link them to each other in some way. But the idea here is let's say that the parent, so this is the stuff you do for the parent right here. I'm sorry, the child. Child does this. Parent does this. Well, what if the child did 5,000 lines of things and the parent did 5,000 lines of things? All of a sudden, we have 10,000 lines of things here to handle whether or not you're the child or the parent. Does that make sense? Okay, so he starts leading towards bloated stuff. This is a system call that allows you to run something at the shell. So this is what does the child do? He's just going to run the ls command, give a directory listing. And what's the parent going to do? It's going to wait for the child and then let us know when it completed. So this is kind of a stupid example of a forking, but well, not a horrible stupid example. Let's say you have a system or a Unix program that's running where we're going to show a directory listing and then do something immediately following this. This would be a mechanism for, this is kind of the observer pattern. Well, this is a predecessor to the observer design pattern where the parent creates a clone. That clone then does an ls to show stuff on the screen. And then the parent waits for that to finish and then goes and does something itself. Maybe it shows the prompt again or something like that. But with linear programming, you might ask, well, why do we need to spawn a parent? Couldn't we have just done the ls ourselves? And then when that command finished, then we'll say, I completed the job of ls. So this is a stupid example. But if you did something major up here, where you really needed some computation running, then you would, this might not be as bad of an example, but this does show us a problem with older computing. And kind of the need for the observer design pattern that I've talked about in some of our other classes. And that's this idea that the observer design pattern says that it's a good idea to always be productive. So it says that don't wait for something to happen when you could be doing something else. All right. So idea here would be is let's forget the current logic that this guy does, but let's say that our child is going to go off and start looking up weather reports someplace. Okay. And we want to know once they have completed the request to find out what's the current temperature in Grafton. All right, and with their internet connection speeds and stuff, that might take, let's say 10 seconds. All right, so in that 10 seconds, we can accomplish a lot in computation, right? So during that 10 seconds, while it's off doing its jazz, we're going to be over here, and we're going to be maybe doing something else. So the parent maybe goes off and it's showing the next screen of your application and stuff like that, and it'll just pop in the current temperature in Grafton once it's available. Okay? Well, in older computing, what we would have to do is we wouldn't even be able to show that second screen until that data came back. All right, so what we would have to do is we would literally sit there and wait. So I might send him off to go get the current weather in Grafton. I'm just going to kind of sit here and just wait for him to finish, because I have nothing better to do. And then as soon as he comes back, then I'm going to spend the time to draw that entire screen out, including the temperature. When I could have been working on the screen, I only needed him for one piece of that screen. Okay, so this is kind of showing us a historical weakness in some of our programming languages and some of our programming constructs where we didn't have that ability to do more than one thing at a time. Okay, so this is kind of our first step towards doing that. So I certainly could have had, I could have had him go and looking up the temperature in Grafton. I could have then been building my next screen, and then we need to have some way for this guy to let me know when he's finished. So this is kind of where I'm assuming here in a couple of the slides are going to start talking about inter-process communication. All right, so because the weakness right here is that I can choose to wait for my child. That's what this wait does right here. But that's our example here where I send you off to get the temperature. I just sit here and twiddle my thumbs, okay, and do nothing. Well, speaking of that, because weird things just pop into my head while. Do you see this new? I think it's a discount double check commercial. It's got Aaron Rodgers in it, and something like the four 4 referees on the field, and I guess they all missed some play, and none of them were watching it or something like that. It was on last night's game. It was the only entertaining part of the game. And the refs all come together at the center of the field and says, "Do you guys see that?" "No, I didn't see it either." "Okay, well you do the juggling ball thing," and so they're acting like they're figuring out like how the play works. So one guy, so you do the juggling ball thing, and you do this, you do that, and then I'll just confidently say it was an incomplete pass or something like that. Then somebody from the crowd yells, and the mic's on. So as they're standing there, have you guys seen it?
The commercial.
Yeah. And then he's talking to Aaron Rodgers afterwards. They're walking out, and he says, 70,000 people just said that. Oh, that doesn't count the 20 million that watched it at home or something like that. So, yeah, I don't know really how that had to do anything with insurance, but it's certainly a memorable commercial. You do the juggling ball thing. I don't know where does that even come from, but it was pretty funny. Are you watching it?
Yeah, I'm sure you did.
First down.
Oh, it's because like the discount double check thing or whatever.
Yeah.
They said,
All right. So the idea here is this shows us a need for something we haven't introduced yet that we will introduce here in a second. And that's this. Well, I assume it's within the next couple of slides. And that's the need for one process to communicate something to another process. Right? So I can either send you off and sit here and wait for you, which we're going to all agree is a waste of time, right? Okay, if we're going to delegate tasks, it would be in the best interest of productivity for while he's off getting the temperature in Grafton, that I'm doing something else productive. And then when he finally has his answer, then he lets me know somehow. Okay, as this is currently written, I literally am waiting on him not being productive, and we're going to say that's bad. All right, certainly possible. And you've actually probably seen this model in some of your mobile applications. So this isn't such a historical type thing. Have you ever had a mobile application on your phone where you clicked a button and you weren't sure whether you clicked it because the whole application just pauses?
Yeah.
While it's doing something, and then all of a sudden, 1, 2, 4, 8 seconds later, if you're on Edge or 1X on Verizon, 5 minutes later, it kicks over to the next screen without giving you any indication that it was thinking, right? So then that's why we have the little spinny thing, right? The spinny thing is, I'm thinking, just wait. That kind of lets you know I pressed the button. That's why the spinny thing exists. Okay. Well, so the idea here is that we'd like things to happen in the background. That's the whole purpose of spawning off a process, quote, happen in the background on a single core CPU. It's not really happening in the background, but it's fooling us, right, the end user. So it at least creates a non-blocking type of situation. In multiple core CPUs, potentially 2 things can be happening at once, or 4 things, or however many cores you have. But punchline here is at the very least the end user, which is kind of what we want to think about from an operating system's perspective, is the end user needs to be faked out all the time. Okay, we should feel like everything is just happening magically and go about our business and all that stuff. Okay, so this is showing us a problem. Okay, that problem is we're making the assumption that this child process has no way of letting us know that it finished. So instead of us going off and doing something else productive, we're literally going to cross our arms and wait. Okay, because at this moment we have direct access to the child. All right, as soon as we let them run off and do their own thing, and we go do our own thing, we've lost this direct connection where we can't just wait. Make sense? So we need to introduce mechanisms for you being able to communicate with me. Because the second we separate, the second you have your own memory space and I have my own memory space, we're now just as good as strangers inside the operating system. We're 2 completely separate processes controlled by 2 completely separate PCBs. We're just floating around the operating system, getting in ready queue lines and stuff like that with really no connection to each other other than the fact that I've remembered that I'm your mommy. See, that got creepy, didn't it?
Not for me.
Okay. Well, it's not as bad as I remember that I spawned you. It actually feels less creepy. That's weird. Yeah.
Well, if you bring in your spawning pool in your
It's true. Let's see. Tree of processes on Solaris. That's stupid. I mean, this is just showing a whole bunch of the different things that are, you know, when your operating system launches, we can all probably, we wouldn't be surprised to know there's a whole bunch of little processes that are running as part of the operating system that we didn't start by double clicking on stuff. Wouldn't surprise us, right? Here's the example of those things with Solaris. An operating system that none of us are.
Netscape.
Is Netscape on there?
Yes.
Yeah, okay, so here's Netscape. Okay, yeah, I mean, well, actually, this is actually a little interesting. This is a little interesting from a tree perspective. So, you know, we have our top-level scheduler. You know, here's 3 different applications that are running. INetD is actually what, this is an internet daemon, which is like a mini internet server, which then has telnet, so somebody's remoted into the system. And CSH is one of our shells. We talked about Bash in here, but I think I probably dumped into a couple of different shells. One was CSH. And inside this shell, they've launched Netscape and they've launched Emacs. Emacs is a kind of a historically popular text editor for programmers. So here's the process ID of each of these guys, and they are children of CSH.
I'm pretty sure in Hackers they mentioned every single one of those.
Really? So these guys are children of CSH. So this would kind of be an example of where forking a child doesn't necessarily have a goal of one program splitting into 2 programs. Okay. Now we have a situation here where this program, CSH, which is a program running inside of the telnet daemon. Okay. I like how they called this one they spelled out daemon, but this one is just INetD. I bet you that there is nothing called telnet daemon. I bet you it's called telnet D or telnet_D. I would have known this years ago, but that's lost. But in any case, CSH is a program that's running, and that program, because the user had typed in Netscape or had typed in Emacs, has now launched another program. In order to do that, it had to fork a child and then associate it with that command. Okay, so just kind of interesting things here, and this is them logging into the system. Here's the X windowing environment, and here's another CSH, blah, blah, blah. Yeah.
What's the correlation between the huge difference in process sizes from INetD and telnet?
Probably the other things that have happened inside the system. So there's probably a bunch of applications or a bunch of PCBs that have been generated between this creating. So this is when the OS first launches, we get an initial, you know, here's our scheduler, here's our, you know, thing that initializes the stuff for the user to work with. But within this, we have some other PIDs that are getting created. So there's probably other things that have happened over here or in the other parts of the operating system that have kind of jacked up the number of processes. So at the very least, it looks like they keep getting bigger as we go down, right? But that's probably not something you can necessarily. You could probably count on these guys having a higher PID than its parent, right? Because they certainly came after their parent. But at some point, I don't even know if you can necessarily count on that. It probably doesn't happen very often, but it's probably theoretically possible for a, well, I know it's theoretically possible because it was one of the major ways that early hackers, let's say, would attack operating systems. You know, I mentioned you can write just a couple of lines of code. I mean, you know, just take this little example, you know, throw this in a while loop. You know, just keep forking children over and over and over again until you run out of process IDs. So what's your number of process IDs in a system? Well, here, we decided that PID_T, they said it was an unsigned, or you said it was a signed integer, right? So in Java speak, that means maximum of 2 billion processes. So once you hit 2 billion in one processes, well, it's actually more than 2 billion in one. It's whatever 2 to the 16th plus 1 is. Okay, whatever that number is, add 1 to it. So 2 to the 16th plus 2, once we got to that number, it would cycle back around and we'd start getting negative PIDs. So there's probably some sort of trap in the operating system that says, if the PID is negative, scream. Something bad has happened, and then your OS starts flipping out and stuff like that. So that's probably your stopping case for allowing more processes to be, that's where this error comes in. So my guess is, yeah, here, if PID is less than 0, if you generated a process ID that was probably negative 2 billion, let's just assume that that's where it comes from. And I think everybody in here, if you've been through the programming classes, you've seen me write something where we probably did it with bytes, where you just keep adding up. So, you know, it's 0, 1, 2, 3, 128, and the next, well, actually 127, and 127 plus 1 goes to negative 128. Then negative 127, 126, 125. So that's how binary counting works. When you get the overflow bit, it goes back down to the biggest negative number. So the byte primitive type, 127 plus 1 is negative 128. Okay, that's just how binary math ends up working. So that's where I'm assuming having a PID less than 0 comes from, is once you have too many processes in the system, you know, it yells. But the idea here is that an int back in C days may not have been 32 bits. It might have actually been 16 bits, but it doesn't really matter. We can just assume it's, in fact, I'm positive it was. 65,535 was the maximum number of PIDs. So yeah, it really doesn't matter in this example. The idea is that once you've hit maximum number of processes in the system, whether it's 32,768 or it's 2 billion and change, bad things happen, right? But bad things had already been happening before that, because we're talking about our process schedulers, right? And our process schedulers say what? What happened? Oh, you found bidgets? Okay, so you know we're talking about this stuff in the context of our process scheduler. So if you're trying to schedule 60,000 running processes on the system, so even though we haven't run out of unique PIDs, if your scheduler is trying to fake out the user as if there's 60,000 programs all running at the same time, we're probably well beyond the point of noticing sluggishness in the OS. Make sense? Okay, so you don't have to run out of PIDs in order to bring an OS to its knees, because eventually you take advantage of how the scheduler works. You know, the scheduler can do a pretty good job of managing, 50, 60, maybe even at 100 processes. We're not noticing huge differences. You start getting into the thousands or the tens of thousands, things are going to go south real quick. That end user is not going to feel so faked out, I think that's the punchline there. Okay. So this is how a process ends up dying. So it executes its last statement and asks the operating system to delete it. So we've actually seen this at some point when I showed you the, I don't know if we did it in here, but did we look at like hello world in assembly language in here? Let's bring it up again real quick. We've looked at it in other classes. Let's just look at hello world assembly. Yeah, this would be a good one. All right, so this is kind of an example of the types of things that would live inside of a PCB. These are our individual instructions, the one-to-one, every assembly language instruction translates into exactly one instruction on the CPU, so we can connect some dots here for us. So this is the hello world program written in Linux assembly. All right, so these are register names, EDX, ECX, EBX, EAX. These are names of registers, and we know registers are our hardware type variables, right? Okay, so all programs begin and end with main. So here's the assembly language version of main. This is where our program starts. And then we also have a data section where the pieces of information live. So in our data section, we have a double byte called hello world. And then we have its length that we're keeping track of. So two variables. Here's the hello world string, and here's how long that string is. And then what are we doing up here? And this involves our system calls. So we are moving the length of the string into this register. We're moving the actual string itself into this register. We're moving the number 1 into this register. And that number 1 correlates to our standard output, which is our screen. Okay, so in Java, this would be system.out. So standard output is the, standard output stream that the operating system knows is our monitor. Then we're moving 4 into EAX, so another register. So we've just filled up 4 registers with things. Okay, and what is 4? 4 is the system call associated with syswrite. Just like fork is a system call, there's a system call called syswrite, and it happens to be system call number 4. So as a programmer in assembly language, you're going to have documentation somewhere where you can go and find the numeric system call, because the operating system, the computer itself likes numbers. Human beings, well, even though this might be a little cryptic, we prefer this over having just a number like this. The reality is that 4 is going to get turned into its binary equivalent, and then the CPU is going to go and look up on it for a magic trick that's equivalent to that. And that magic trick is going to map to a function on the operating system that actually goes and does something, quote, awesome, let's say. Okay, so what have we done in these 4 lines? We've just staged data. We've moved 4 pieces of information into 4 different registers. That's it. Nothing has actually happened yet. All right, we just moved crap into registers. The next line, we have an interrupt. So this is where this dude jumps off the CPU. Okay, so this kind of links up to that slide a couple slides ago when we talked about different ways we can leave the CPU. We've been interrupted for I/O stuff. We've run out of our time slice. We're forking a child, whatever, different situations. So we are now interrupting. This program's interrupting because it has to go do I/O stuff. This is the way that we call upon the kernel. Kind of like, I have staged the situation. These registers have the current values that you've required from me. So essentially, this is a function that requires 4 inputs, right? Well, actually, this syswrite requires 3 inputs. It requires a length, what you want to write, and where you want to write it. Okay, so 3 different inputs. Here's the system call. When we interrupt the kernel, when we interrupt the CPU, it's going to jump to the kernel. Kernel's going to look at what system call you want to call. It's going to say, oh, syswrite, I require 3 inputs. I should find the length inside of EDX. I should find the string inside of ECX. I should find the where you want me to write it to, the output stream inside of EBX. It'll grab those 3 things. It'll then perform the system call, writing it out. And then this guy will go and get back in line. He'll get back into the ready queue. And when he gets back to the CPU, he's going to run back in. He's going to unpack his bags. And what's the very first thing he does? He moves into this. So here's one instruction he'll do. He'll move 1 into EAX, and 1 is associated with the system exit system call. And notice that EAX here is equivalent to the EAX up here. So that register is where we hold system calls. That's the guy that holds the system call in Linux. So every single time we interrupt the CPU, we're going to go and look at EAX to find out what is the thing that this process wants to do. Okay? So if it's a 4, that means he wants to write something. If it's a 1, that means he wants to exit the system. Program's done. Okay? So we loaded a 1 in here. Then we interrupted the CPU. CPU will go and look at EAX and see, oh, this guy wants to exit, so we'll go into that termination thing because this process is dying. Nothing else to do. Make sense? So this is kind of what's happening behind the scenes inside of our operating system. So hopefully this kind of brings a little bit of context to kind of what we're talking about.
So where is Hello World actually written? There?
Well, this is a variable. So we have a variable called message that holds Hello World. Where does it actually get written to the screen?
Yeah.
Right here.
Okay.
Okay, so the idea is so if we kind of look at this as a real life example, okay, I'm going to tell this Nick, I'll say, you need to remember the length of Hello World. Okay, I'll tell this Nick, you have to remember Hello World itself. All right, that's what you're in charge of. So you're EDX, you're ECX. Let's see, who's responsible? Levi. So Levi, you're okay. Levi, you're remembering that the system call we're going to do is standard out. Okay. We certainly would have had Doctor remember if it was fork. So in any case, we're going to do so you're standard out. That's the system call. All right. So now Actually, no, you're not the system call. You're the output streams. You're remembering where we're writing this stuff. Okay, and then Austin, you can be the system call. You're syswrite. Okay, so you're the actual system call we're going to call. All right, so now we've interrupted the CPU. So the very first thing when the CPU interrupts, it dives down to the kernel. So I'm the kernel, and I say, okay, Austin, what is it that you wanted to do? You're up. What are you doing? You're EAX. What are you supposed to remember? You're this guy. What are you remembering? Man, this is a sluggish operating system. You're remembering this. You're EAX. You're going to tell me 4.
What does 4 mean now?
It means syswrite. This is the comment that's over here.
Okay.
So I happen to know, I have a little lookup table down here, that when you say, oh, 4, okay, because that's where we're going to store the system calls, I know, okay, 4 is, that's syswrite. Okay, so what do I need from syswrite? I need the length. What's the length? You're going to give me the length. Okay, I need the string. You're going to give me the string. Okay, I need where I'm going to write it to. He's going to give me where I'm going to write it to. So those are the 3 pieces of information I need. And I know that one of the pieces of information will be there, there, and then there. So now I've gathered the 3 inputs for that function. And now I can actually go and execute the syswrite system call.
I think what's confusing me is that section data, that entire section, is beneath everything else.
Yeah.
Because I feel like it should be defined first.
So why does that matter?
Because it doesn't know what length is or what message is.
Well, clearly it does because they're using them up here. So can't there just be a thing in this language?
I guess.
Yeah, I mean, I guess I wouldn't get too caught up in that. I mean, what ends up happening is in an assembly language thing, it's going to go through the data section first and kind of read in these symbols so it has them.
So it's not chronological.
Yeah, but that really, let's say that's true, but that's kind of insignificant in kind of what we're looking at here.
Okay.
Okay, so just assume that we have 2 variables, one called message that holds hello world and another one called length that holds the length of hello world. We just happen to have 2 variables. It doesn't matter whether they were defined here, defined up above, or just fictitiously came into existence. Okay? Punchline here for us is this is how operating systems work. Okay? We stage some registers, then we throw in the system call, then we ask the kernel to execute what we just staged. So I go and look at system call first. You've told me essentially that I need 3 pieces of information, and specifically because you told me it was syswrite, I know I'm going to grab my information from you, and you. And I'm going to go and do whatever I do. Make sense? Then I know we're out of time. So let me, then we're going to go get back in line for the ready queue. Because now we've done our I.O., we're no longer waiting. We'll get back in line. We'll move exactly 1 system call into Austin. So now Austin's remembering sysx, sysexit, and then we'll interrupt again, and you'll tell me, oh, it's system call 1. I'm like, oh, that means that you are now dying as a PCB. Okay, this process is now done, so go through the death process. Make sense? All right, I'll see everybody on Wednesday.